For this video, we are going to perform dot na product in a vector and vector, a matrix and vector, as well as a matrix and matrix. So in order for us to do that, we can use the nt.dot na excuse me, the dot na function of enumpy. Okay, so suppose we have an array A with 3 elements 0, 1, 2. So taking the dot product of A and by itself, that will give you a scalar na value. So as you can see here, suppose we have this one matrix or one vector and we multiply it with another vector. Okay, and so in programming jargon, it should be an 1D na array multiplied by another na 1D na array. So what restriction that you can see here is that the number of the components of one vector should be equal to the number of components of another na vector or array. Okay, so what we are doing here is we perform element-wise multiplication between the two and add it up. So it's a fundamental way of combining information from the two na vectors, which is very important in machine learning. Okay, let's have this example. So in here, we are performing dot product of A by itself. So what we are going to do is to multiply A element twice with the elements of A also. So, and then we add them up. So 0 times 0 plus 1 times 1 plus 2 times 2, that gives us a scalar value, which is 5. Okay. And what if we want to multiply a matrix and a vector? Suppose we have the M. The M has 3 by 3 na dimension, so which is a matrix. And a vector, on the other hand, is a one-dimensional. Okay, so A has elements 0, 1, 2. So we want to take the dot product of a matrix and a vector. So as you can see here, let us try to understand this first. We have a 2 by 2 na matrix, and then we have a vector. And what you can see is that the number of components here or row of a matrix should be equal to the number of components of the vector, right? Because we are multiplying the row of this matrix to the column of the vector, okay? And so what we are going to do is, first is we take here the multiply or take the element-wise na multiplication of row 1 by the vector. So that is A times X plus BY, B times Y. And then after that, the second na row of the matrix times the vector. So C times X plus D times Y. So let us try to understand it with an example. We have the matrix M and with values 147, 250, 369. So it is 3 by 3. While the array A is one-dimensional with 3 elements. So as you can see, the number of rows here is basically equal to the number of components of the 1D array A, which makes this calculation valid, okay, or allowable. So we perform an element-wise multiplication between row 0 or the first row and the corresponding elements of A. So for instance, here we have 1 times 0 plus 4 times 1 plus 7 times 2. So that gives you a scalar na value 18. And moving on to the next row, that's 250 multiplied to the corresponding elements of A. So that will give you 2 times 0 plus 5 times 1 plus 0 times 2, and taking the resulting to a scalar value of 5. And lastly, the last row of M and the corresponding elements of A. So that will give you 3 times 0 plus 6 times 1 plus 9 times 2. So the resulting the dot product is 18, 5, and 3. Okay. Now, what if we want to multiply, to take the dot product of two matrices? Okay. And the M here, the M has values 147, 250, 369, and we will take the dot product, its dot product with itself. Okay. So here's how you can visualize it when you multiply it with two na matrices. So we will each of the rows of matrix 1 will be multiplied to each of the columns of matrix 2. Okay, so at first, here the row 1 is multiplied element-wise with the column na 1 of matrix 2, and we take the sum. Okay, so we have AW plus BY. Now, for the next is that the same row 1 multiplied element-wise with the second na row. Okay, so, and we take the sum. So we have AX plus BZ. And next, naubos na natin yung number of columns dito. So we will move on to the next na row of matrix 1. So we have the matrix, row 2 of matrix 1 times the column 1 of matrix 2 multiplied element-wise. So that will give you CW plus DY. And after that, the last na operation is that we take the element-wise multiplication of row 2 of matrix 1 times the column 2 of matrix 2. Okay, so it will give you CX plus DZ. Okay, so let's have an example. Earlier, I have shown you that we took the product or the dot product of matrix M with itself. So we are basically multiplying a 3 by 3 na matrix with another na 3 by 3 na matrix. So this is the result. The final na result is also a 3 by 3 na matrix. So how did we come up to this result? So let us see how it was done. So we have the matrix 1 multiplied by itself. So we just renamed it M sub 1 and M sub 2. Okay, so as you have shown here, so we will start with the row 0, or the row na first na row multiplied element-wise with the column 1 of M2. Okay, and take the sum. So that will give you 1 times 1 plus 4 times 2 plus 7 times 3. Okay, next, still here, row 0 or first row in column 2 of M2. Okay, that is for this position. And for next row, row 1 or row 0 or first row times the column of matrix 2. Okay, now that we are done with the number of columns, we move on to the next na row. So we have that second row or the row 1, 250 times the column 1 of M2. Next is the, for this cell, we have the still on the second row of M1 and the second the column of M2. Next is the 250 times 709, which refers to the second na row of M1 and the third na column of M2. And lastly, for the third na row, we have the 369 times the first na column and so on. Okay, so if multiplying two matrices, it is important that the number of rows of the matrix is equal to the column of the second na matrix. Okay, so the number of rows should be equal to the number of columns. All right, so for instance, in here, we tried to have oops. We have an array M, right, which is 3 by 3. And we have generated another array N with size 2 by 3. Okay, so we take the dot product of M and N, but this will result to an error. Okay, why? So as you can see, it says that the shapes of 3 by 3 and 2 by 3 are not aligned. So what we can see here is that the number of columns of M do not match with the number of rows of the N. Okay, so M is 3, has 3 rows and 3 columns, and N has 2 rows and 3 na columns, and they do not match. Why is that the case? Because we are taking the element-wise na multiplication of this na row and this na column. Okay, so there is walang value to be multiplied to the 7. So they do not match and therefore cannot be performed. All right, so it is important that this will match. So now let us have an example. Suppose we replace the value of N. Now the N has a shape 3 by 2. Okay, so the N has a shape of 3 by 2. And we will take a dot product of M and N. So M has a shape of 3 by 3. So it gave us this dot product. So final na result, final na dimension, or final shape is 3 by 2. So how did we come up to this result? So let us see here. So we have this matrix M, which has a size of 3 by 3. And we have another N, which has a size of 3 by 2. Okay, now that the number of columns of M and the number of rows of N are matching, then that means that the operation may be performed. So now we are going to show you how to compute the values. So we start with the row 1 multiplied with the first row of M and the first column of N, and then take the element-wise multiplication and take the sum. So that gives you 48. Now for this, we are taking the M and the next na column of N, which is 1, 4, 7 times 2, 4, and 6. So that will give us 60. Now we will move on to the next na row. So the second na row of M times the first row of N, that will give us 17. Now the second row of M and the second na column of N, that will give us 24. The third na row of M plus the first na column of N, that will give us 66, and the third na row of M and the second na column of N, which is 84. So you are basically just iterating. You can think of it like a for loop. So for row, then iterate with the number of columns of another na matrix. Okay, and then once you're done with the number of the columns, then you move on to the next row and you iterate again with the number of columns of the second na matrix. And once you're done, you move on to the last na row. Okay, and iterate again to the number of columns of the second matrix.